So this is energy set number 4, and it asks about the difference in a sphere and a cube on a ramp where the mu value is 0. Specifically, it's asking which one reaches the bottom first. And I'm going to choose that they both reach the bottom at the same time. Why? Well, the mu value equaling 0 means that there is no friction force. If there's no friction force, then our hoop, or solid sphere, I guess, can't roll, and so it's just sliding down. So the velocity of the center of mass is straight down the ramp for each one. There's no difference in the cube and the sphere. So then it asks me to find the final velocity at the bottom for whichever one, for both of them. So at the beginning, each object, both the cube and the sphere, can be described with potential energy. At the end, because there's no rotation, each one of them only has translational kinetic energy, 1/2 m v final squared. So we can cancel our m's, and we can find the final velocity as the square root of 2gh. Here we're accelerating uniformly, which means that we can think about this as the final velocity. The average velocity would be half of that in the initial velocity, like right in between those two numbers. So that will let us know that this being the final velocity, the velocity is gained uniformly from 0 up to that number. So therefore, whoever has a larger velocity has a larger acceleration and is going to complete this distance first. Yeah. So with that, let's move on. The solid sphere and the cube begin at rest. Now the cube is on a ramp, it's frictionless. So we're going to divide the ramp in 2 ramps. And this side is still going to have a mu equals 0, but this side will have a mu value. And the mu value on that side, we don't know it, but it's such that the sphere is going to roll without slipping. Now which one reaches the bottom first? So the cube is just sliding. Well, the sphere is sliding, rolling. I guess sliding is not really the proper word. This sphere is translating and rolling. So we can break our two thoughts up. The cube has no frictional loss, or no friction at all. So the acceleration of the center of mass is just g sine theta. Well, for their hoop, the acceleration of the center of mass won't be just g sine theta, because there's friction force acting backwards. So therefore, the block is going to reach the bottom first. Block. Because there's just no friction, and no friction is always faster than when there's friction. So it then asks us to define the velocity for each one. Our velocity for our cube is exactly the same as earlier in the video, mgh equals 1/2 mv squared. So that's that. Our velocity for our hoop is going to start out the same way, mgh, but our hoop ends up translating and rotating. And I keep saying hoop, but I really think it's a solid sphere. I'll check really quick. Yep, solid sphere. Why am I checking now? Well, as I wrote the I value, I wanted to make sure I had the right coefficient. So I'm just going to expand on the statement I have. Not that I've done anything wrong, I can just make it more beautiful. So I looked at my chart, and I know that a solid sphere is 2/5 mr squared. And then I'm going to replace omega with v over r. Each one of those must be squared, because it's omega squared. At that moment, I realize I can cancel those r's, and I can cancel m's. And so here I have gh equals 1/2 v final squared plus 1/2 of 2/5, 1/5 v final squared. So I can add those together. 1/2 plus 1/5 is 5/10 plus 2/10, 7/10. So I can solve for the final velocity. It's the square root of 10 over 7 gh. So as you can see, 10 over 7 is not as large as 2. So our block will be going faster, our hoop will be going slower at the bottom, and again we gain this uniformly. Now the extra credit part of this problem asks what is the coefficient of friction to make this happen. So if we want to find out what actually is the mu value over here on this ramp for perfect sliding, we're going to need to go into a forces mode. So we're going to need to draw our hoop and figure out what the forces are that act on our hoop. So, sphere. Guess I have a bias against spheres. So here we have mg, straight down. We have the normal force, straight up from the ramp, perpendicular to the ramp. Then we have friction force opposing the velocity of the center of mass, also causing the torque. You can see this as an omega, like that. That's how it's rolling. This is our angle theta down here. It's best, just like we do any problem, to think about mg in terms of its components. Or that's our angle theta. So that makes this down here mg sine theta. And this one here, mg cos theta. So to think about this problem, we can sum torques and some forces. So first let's do what you already know how to do, which is sum forces that are perpendicular to the ramp, quote, in the y direction. With that, we know that Fn will equal mg cos theta, because there's no acceleration in this direction here. And then we'll sum the forces that are parallel to the ramp. This will be a little bit more complicated. We have mg sine theta pulling down the ramp. We have friction force going up the ramp. And that will equal ma. And so here we actually know A, and so we could probably solve for frictional force. And then we can relate friction force and normal force together. So let's use our result from before and solve for A. I suggest we do that using the v final squared equals v initial squared plus 2a delta x. So here is our x value, which using geometry, we want to express this distance x along the ramp like this in terms of the height. This is the angle theta down here. We can write that x equals the height divided by sine theta. So there's a little trig identity there. So with that, let's write v final squared, so squaring the result we got, equals v initial squared plus 2 times the acceleration, which we're going to put in there, times our actual distance, which is x. But instead of x, I'm going to write h over sine theta. So here I'm going to solve for a, and I'm going to find it's 10/7 over 2, so 5/7. G, h's cancel, sine theta. Okay, so with that I'm going to put that in here. So instead of ma, I'm going to say equals mg sine theta times our coefficient of 5/7. Okay, so I'm going to solve for friction force. So add it to that side, subtract that. So 1 mg theta minus 5/7 of an mg theta simplifies to 2/7 mg sine theta. And if we just take that and we divide by our normal force, which we found above, which is mg cos theta, we realize our mg's are going to cancel, and we discover that this is mu. And so the mu we need is 2/7 tangent theta. Beautiful. So that's the mu value that's required to make our solid sphere roll perfectly down the ramp. Our solid sphere will take a longer amount of time because there's friction, while our cube will take less time just simply because there is no friction. Enjoy.